Okay, thanks. So I'm giving this talk remotely, and so is Courtney dressing there?
Yes.
Hi. So Courtney's going to help me out by giving me some audience feedback, since I can't see you and you can't see me. And so to start out this talk, which is kind of about microlensing and technique, I'm going to start out by talking about theory. And just so you know, you shouldn't all go to sleep or start checking your email, because there will be a quiz. Okay.
They're all paying attention. You're good.
Okay, good. Thank you. All right. So normally, light from a star travels directly to us in a straight line. But if there's another star between us and the more distant star, then we see the light is bent. And if the bending is strong enough, the light gets split into two images. And so you see what I did there? I used the word strong bending. And so microlensing, anytime you see multiple images, that's strong gravitational lensing. And microlensing is just a subset of general strong gravitational lensing, which you've probably heard about in the context of the Einstein cross. And so you just remember in your mind that microlensing is the exact same thing, but involving stars rather than galaxies. If there's a planet around your star, that planet also bends light, and so you get an extra effect due to the planet itself. This is sort of a cartoon side-on view of it. This is the face-on view of microlensing. You have the lens star, which is in the foreground, the source star, which is very far away from it, in the background, and then the two images of the source. And if the source and the lens are perfectly aligned, those images grow and they merge and they form a perfect ring called the Einstein Ring. And the Einstein Ring is a really important scale for microlensing because it sets all of the fundamental scales. So pretty much everything is measured relative to the size of the Einstein Ring. And the Einstein Ring, how big it is, depends on your lens and how far away it is. So the projection of the Einstein Ring onto the observer plane is typically about 10 AU for, say, a solar mass star at 4 kiloparsecs. If your lens is smaller than that, if it's an M-dwarf or a planet, the Einstein Ring is smaller. If the lens is closer to you than 4 kiloparsecs, the Einstein Ring gets smaller. And if it's farther away, the Einstein Ring is larger. And so the size of the Einstein Ring depends on what your lens is and where it is relative to your position. In an angular sense, the size of the Einstein Ring is typically 1 milliarcsecond. So the angle that it subtends is 1 milliarcsecond. And that creates a problem, right? So first, in order to see microlensing, your source and your lens need to be aligned to better than 1 milliarcsecond, right? And that's hard to do. The source and the lens stars are completely unrelated stars. They have nothing to do with each other. They're kiloparsecs apart from the galaxy. And somehow they have to appear to come into alignment by better than 1 milliarcsecond, which is hard and extremely rare. And in fact, it's so rare that when Einstein first wrote about microlensing in 1936, he said, even in the most favorable cases, there is no great chance of observing this phenomenon. No great chance. So he just wrote this and he was just like, we're done. You know, I mentioned it, we discussed it, we're done. The second thing about this 1 milliarcsecond is that 1 milliarcsecond, you can see that that's about the separation between the two images, right? And so 1 milliarcsecond is 1,000 times smaller than a seeing limited image of a star. 1 milliarcsecond is still a factor of 10 smaller than the best you can do with AO, with adaptive optics imaging. 1 milliarcsecond is really small. So we actually have two problems with microlensing. Because the Einstein Ring is only about 1 milliarcsecond, microlensing should never occur, and the images can't be resolved. There's two really serious problems. Really serious problems. But fortunately, there are solutions to them, which is why we can have this conversation today. So first, you should never say never. And second, lensing also magnifies the source. And so if you look at this animation, what you see is the source star passing behind the lens. You see the two images that they change as a function of time. But you also see in the bottom panel that the magnification is changing as a function of time. And that's key, because we can observe the change in the magnification as a function of time. And the width of the observed light curve is the Einstein timescale TE, and that's directly proportional to the size of the Einstein ring, which will become important later. If we have a planet around our lens star, let me play this movie, then we get an additional perturbation due to the planet. And so we can detect planets. And so that's what's going on in the underlying phenomenon, the physical phenomenon of microlensing. But the theme of this conference, this workshop, is there a planet in my data? And so the thing I really want you to be able to take away from this is the ability to answer that question, is there a planet in my data? And so in order to answer that question, you need to be able to say, well, given the light curve I observe, is there a planet there? And so I think the most intuitive way to understand microlensing and whether or not there is a planet is to talk about the magnification map. So this is a magnification map for a single lens star. There's a lens star in the very center of this map. And it tells you what the magnification of a source should be at any point relative to this lens star. And so what you can see from this is that for a single star, it's radially symmetric, which reflects the spherical symmetry of a star. And you can see that it gets brighter as you get closer to the lens. And actually, in particular, if you went exactly to the position of the lens star, you would get infinite magnification. So the magnification diverges to infinity at the position of the lens. And so then a source is moving relative to the lens. So as the source star traces a path across this map, you see a magnification curve or a light curve of the microlensing event. And if the source passes closer to the lens, that overall magnification curve is brighter. If I then add a planet around my lens, it perturbs the map, but not in kind of the way you would expect. So you can see the planets on the right, but the distortion to this map is primarily off to the left, right? But you can see that the lens star itself is still dominating the overall magnification map. It's still true that as you get closer to the lens, you get brighter. But the planet has added a perturbation, and actually in these areas highlighted in red, in all of those areas, the magnification diverges to infinity. And so those red areas are the caustics. And if the source passes over one of those caustics, you get a perturbation due to the presence of the planet. And the caustic structure is really important for understanding microlensing. So there are first, you get two sets of caustics from a planet. One is the planetary caustics on the left. And those can show up on the left, they can show up on the right, they can show up closer and farther, and that all depends on the exact location of the planet. But you also get a central caustic. And so the planet always produces a central caustic at the position of the lens star itself. And I'm going to blow up the central caustic so that we can see it a little better, and use this to illustrate general properties of the caustic. Well, first, the caustic is a closed curve. All right, you see the red shape here, polygon, is the caustic itself. That's where the magnification diverges to infinity. All right, and so the magnification diverges into infinity there, and actually the caustic it's a mathematical object, and so it's actually the width of the caustic is exactly zero, the way that the width of a true mathematical line is zero. And so outside the caustic, it has finite magnification, but along this perfect edge, there is infinite magnification. And that's important for microlensing, because if your source crosses the caustic, it's crossing this sharp edge. And so you get a very distinct feature in your light curve. You get a discontinuous slope. You see an edge in the light curve that tells you that a caustic crossing has occurred. Okay, so other things about this. Well, the cusps, which are all the points of the caustic, this caustic has 4 points. the cusps increase the magnification nearby. So to detect a planet, you don't necessarily have to cross the cusp or cross the caustic itself, but you can just pass nearby one of these cusps, and you can see the magnification is enhanced sort of near the caustic in the cusp regions. And then in addition to that, on the left, there's a demagnified zone, which you can't really see on this scale, but if I zoom out to the full caustic map, again, you can see on the far left there's a darker region. And so in this darker region, if the source passes through that darker region, you'll get a dip in your light curve. And these dips are very characteristic of planets. And so if you see a dip in your light curve, you know that it's due to the presence of a planet. But not all planets produce dips. So in the cosmic scheme of planetary perturbations, all dips are planets, but not all planets have dips. Okay, so last thing to know about caustics and magnification maps, which is this is the magnification map of the central caustic. Often in a paper, all you'll see is the caustic. That's all that's shown in the paper. So you have magnification map, caustic. And it's just expected that the reader will be able to infer the entire magnification map structure by just seeing this caustic. And so you have the basic tools that you need to understand this. First, the magnification diverges to infinity at the caustic. Second, you've got this demagnified zone off to the left. And third, you have these cusps, and at the cusps you get sort of enhanced magnification. Right? And so those are the major features of a caustic. And so by seeing a caustic diagram, you should be able to infer the existence of, or the entire structure of the magnification map. Okay, so what does an actual microlensing event look like? Well, this is an example of an event from the Korea Microlensing Telescope Network, and this was taken in 2015. And what you see is you can see the main microlensing event lasts for a period of about 40 days. And so this is the effect, the microlensing effect due to the star, due to the host. But on top of this 40-day timescale event, you see this feature, this perturbation, and this is the perturbation due to a planet. And in particular, you see that it's got a 12-hour timescale, and that you see the caustic crossing quite clearly. And so you have this sudden sharp edge in your light curve corresponding to the edge of the caustic. And so if we return to the magnification map, all right, the star is in the center. The planet is off to the right on the slide. It doesn't fit in, it probably doesn't fit in the room. But you have this caustic structure, and then as the source crosses the caustic structure, you get a caustic crossing when it goes into the caustic and a caustic exit when it comes out. And from that, you detect the planet. This event also illustrates another thing about microlensing, though, which is that we're dealing with many different timescales. You have the underlying stellar event, which lasts for 40 days. You have the planetary event, which lasts for 12 hours. And you have the caustic crossing, which lasts for 30 minutes. And so in order to do microlensing effectively, you need a wide field survey that's continuous, a continuous wide field survey. And that's also the reason why we can detect microlensing events all. This is why we should never say never. This is a picture of the ogle 4 camera of field 505 from the ogle 4 camera. The camera itself covers a view that's 1.4 square degrees. And you can see there's lots and lots of stars here. But in 2016, only 100 of those stars underwent microlensing events. And so microlensing events are very rare, and you have to look at a lot of stars to see them. You need to look at them often in order to capture these caustic crossings and planetary perturbations and to characterize them. And in addition to that, if your planet perturbations are only 12 hours, then you have to be lucky to see it from any particular telescope site. And so you really want telescopes that are distributed all over the world. And so the main wide field microlensing surveys are the ogle survey in Chile, the MOA survey in New Zealand, and those have been going on for decades or more. And then last year, the Korea Microlensing Telescope Network was commissioned, and that has 3 sites in Chile, South Africa, and Australia. And so that's just a practical matter of microlensing. Okay, so now for the quiz. Is there a planet in my data? So I would like to know from you all, how many people think there is a planet in this data? Please raise your hand.
I think maybe a third of the room is raising their hands.
Okay. How many people think there is not a planet in the data?
This is an even smaller number, maybe 10 people. So there are lots of people who did not vote.
Okay, so there are lots of people who did not vote. Well, I kind of understand that because it's hard to tell from this data, because there's only about 1 point taken every night, which we already know from before is not enough to detect planets. Fortunately, there's a lot more data on this event. So now, how many people think there's a planet in this data?
Basically everybody.
Basically everybody. Okay, yes. There is a planet. It's right there. I hope that's the one you saw. If you saw a different one, you should let me know later. Okay? And that's the planetary perturbation. This planet has a mass ratio, which is the mass of the planet divided by the mass of a star, of 7.6 times 10 to the minus 5. And in case that's sort of a meaningless number to you, for reference, the mass of Neptune divided by the mass of the Sun is 5 times 10 to the minus 5. So it's a very small planet. And it's there. Okay, so now I have another question. Is it a planetary caustic crossing or a central caustic crossing? So who thinks it's a planetary caustic crossing?
10 or so people.
10 or so people. Who thinks it's a central caustic crossing?
2, 3 people.
2. Okay, so we have not internalized stuff about caustics yet. That's okay. You can keep thinking about it. This one is a planetary caustic crossing, and you know it's a planetary caustic crossing because it's off to the side of the light curve. Central caustics are at the position of the lens star, and so if you have a central caustic perturbation, it would occur at the very peak of the light curve, sort of around 3582. So central caustic crossings occur at the peak of the light curve, planetary caustic crossings occur sort of somewhere else. That's the basic intuitive way to think about that. All right, next question. I have 4 light curves here, 4 microlensing events. How many planets do you think there are? So you should hold up a number of fingers between 0 and 10. I will tell you there are fewer than 10 planets. So, yeah. So a number of fingers between 0 and 10. How many planets?
I'm seeing lots of numbers between 2 and 5.
Okay, lots of numbers between 2 and 5.
And a couple ones.
Okay, and a couple ones. All right. These events are very special events because you can see in the magnitude scale that they're all magnified by at least 4 magnitudes. And so all of these events have magnifications of 100 or more. And so I'm going to focus on the very peaks of these events because that's where you expect a central caustic crossing should it exist. It should exist at the peak. And so these are the peaks, the very peaks of these events, and you can see that these peaks are lasting about 0.2 days. And for the bottom panels, I'm going to show you the residuals. All right, so before we had a few 1s and then some numbers between 2 and 5. Now, how many planets do you think there are in this data?
Oh, hey, do you know how long she is going to be?
Okay. How many? Raise your hand if you think there's 1 planet.
Okay, thanks.
2, 3, 4, 5. Okay. Looks like 3 or 4 is probably the consensus.
3 or 4 is probably the consensus. Okay. Thanks. The answer is that there are 2 planets. And the planets are all on the left. In the upper left-hand panel, you can see that it's clearly kind of messed up. And that's a caustic crossing from the planet. In the lower left-hand panel, you can see in the residuals these funny little bumps. And those are from a planet. So the 2 on the bottom and the 1 in the upper right have something in common. Because in this case, the lens is directly transiting the face of the star. And so in the lower left-hand panel, what's happening is that the caustic is much smaller than the size of the source star. And so you get a perturbation when the caustic passes onto the face of the source, and then it's on the face and it's not doing anything for a while, and then you get another perturbation when it passes off the face of the source.
Hello. Okay. So,
just let you know, we are taking care of the line noise, so it'll be resolved soon.
So would you please tell me exactly what you told a gentleman at JPL Security?
Sorry, are we okay? Alright. Okay. And then the lower right-hand one is just like the lower left-hand one, except that there is no planet. So you can see the residuals are flat. The upper right-hand one, I was kind of mean. And you can see in the I-band data that there are these bumps and wiggles. And we actually originally, when we discovered this object, when we first observed it, we thought there was a planet there. But what you see is actually in the H-band data that there are no bumps and wiggles. The H-band data themselves are smooth. And so in microlensing, lensing affects all wavelengths of light equally, so it's achromatic. And so if a signal is due to lensing, it should be visible, it should be the same in both I-band and H-band. And what we see is it is not the same, therefore that signal must not be due to microlensing. And what we actually see here is what we're seeing is the differential magnification of star spots on the surface of the source star. So that was me and I've made a mistake in there, but okay. Oh, come on. All right, here we go. Okay, so here's another light curve. I guess, all right, so how many planets are in this light curve?
3, 2. Any 4s? Sold, the woman over there. All right, 2 and 3, Jen.
2 and 3. Okay, so the answer is that there's 2 planets, and I realized that I left the thing that says triple model on there, which is, kind of a giveaway. So, but maybe that's what led, that might also lead you to think that there are 3 planets. So triple, when you describe a model, if it says triple, that means there are 3 bodies, and one of those bodies is the star itself. And so in this case, there are 2 planets. 1 star, 2 planets, that makes it a triple model. You've got a mass ratio of 7.8 times 10 to the minus 4 for that big one. And then you have a very classic dip structure, which we know must be due to a planet, from a slightly smaller planet. And so there are 2 planets in here. And what's cool about 2 planets is that if you look at the caustic structure looks pretty much like the superposition of the planets individually. And so that's pretty cool. All right. And so up to this point, I've told you about a bunch of planets, planet discoveries with microlensing. Microlensing finds single planets, it finds double planets, could potentially find triple, 3-planet systems. But so far, I've only talked about these planets in terms of their mass ratio. And I talked about them in terms of their mass ratio because mass ratio is our primary observable in microlensing. And I think at other points during this conference, you've also talked about radial velocity and transits. And they tell you that they measure the mass of the planet and the radius of the planet, but that's not actually true. Their fundamental observables are also quantities that are measured relative to the properties of the host star. The difference is in radial velocity and transits, they take for granted the fact that the properties of that host star are known. They take for granted the fact that the mass and the radius are known. But we can't do the same for microlensing. And the reason is illustrated here. So it might seem outrageous that you can't characterize the lens star in detail because you can see in the left-hand panel an actual image of a microlensing event which is full of photons. There's a ton of photons right there in the middle of that red circle. But the problem is that those photons, the magnified photons, are all from the source star, which tells you nothing about your planetary system, except that the shape of that light curve tells you about your lens. And so the information you get about your lens from the light curve itself is primarily in the form of the Einstein timescale, TE, which we know is equal to the size of the Einstein ring divided by the relative motion, the velocity. It's just radius divided by velocity. But we know that the Einstein ring depends on both the mass of the star and its distance. And so you have one observable and 3 unknowns, which is quite obviously a bad situation to be in. And so the question is, how can we measure more things so that we can characterize these lens stars and measure their masses? And so one thing you can do is measure finite source effects. So if you remember this event, you have a caustic crossing, and you'll notice that you don't actually observe the magnification going to infinity over the caustic crossing. What you see instead is you see the size of the source, because it has a finite size, you see that source crossing the caustic, and so the width of that caustic crossing reflects the size of the source, and that gives you a ruler, and so then you can measure theta e, the angular size of the Einstein ring, from that. And so the mass of the star is related to the angular size of the Einstein ring divided by the microlens parallax. So now we have 2 observables and 3 unknowns, so that gives us a relationship, which gives us this mass-distance relationship from theta e. So that's one piece of information we can get. Another piece of information, well, we need a second piece of information. So if you think about this event, which I showed you earlier, that width of that feature, that peak, gives you theta e. But we can try to measure the lens flux itself to give us a third piece of information. And so when it's magnified, you get source photons. When it's not magnified, you find out that it's hard to measure the flux of a star at 4 or 6 kiloparsecs with a 1.3 meter telescope. Virginie Battista observed this with Keck adaptive optics, and which both resolves out unrelated stars and lets you measure very faint objects. And so from this measurement of light, she was able to take the measurement of theta e for the Einstein ring, that relationship, combine it with the measured light relationship, and get the mass and distance of the lens. And so she finds out by making these measurements that the mass of the planet is a number. It's 4.8 Jupiter masses, and it's orbiting a K-dwarf. Another thing that you can do if you can't measure the light is to try to measure this second variable, the microlens parallax. And so microlens parallax is great. It works just like regular parallax. You observe the same object from 2 different locations. You see a different perspective on that object. You see a different alignment between the source and the lens star, and so you see different light curves from the Earth and Spitzer. And so the first campaign to measure microlens parallax was in 2014. All right, how many people think there's a planet in this event?
Hands up for planets. We've got a handful of votes for planets, mostly no's.
Mostly no's, okay. Well, there is no planet in this event, but there is a very clear parallax signal, which you can see from both the difference in the amplification and the difference in the timing of this event. This is another event observed by Spitzer, planet or no planet.
Planet, no planet. Say half the room says planets.
Okay, yeah. So this one does have a planet. I think you're getting better at this. All right, that's a planet. This width gives you theta e. This offset gives you pi e. You combine pi e and theta e, you get a mass for the lens star. The mass of the lens star gives you that it's a 21 Earth mass planet around sort of M dwarf. And so by combining all of this information, we can get more information about the planet. And so that's pretty much the important stuff about microlensing. To interpret a microlensing light curve, you have that the caustics determine the light curve, and you have 3 different ways that you can constrain the true lens mass so that you can measure the true planet mass. So you have theta e, you have finite source effects, parallax, and flux. And I focused in this talk on a qualitative understanding of microlensing, but there's a lot of physics and mathematics underlying everything I've said. And so if you look online, the last slide in the talk has some basic resources about more of the theory and the mathematics of microlensing. And so the things, sort of favorites of mine, are highlighted in bold. And that's it. And so I will take your questions now.
Okay. Jen, we have a question about whether you can see light from both the source star and the lens star, and if so, how you would separate the light from the 2 stars. Is that a good summary?
in general, what we do is, well, there are two things you can do. So normally, if you just have normal seeing limit ground-based imaging, you have no idea how many stars. You have light that's changing, and that's light from the source, and then you have light from other stuff. And that other stuff includes the lens, but is not exclusive to the lens. So if you look at like the lower right-hand corner, you have like that bar for 1 arcsecond, and you can see that in any 1 arcsecond PSF, you're going to combine the light from several stars. And so when Virginie made her measurement, what she measured was the combined light from the lens and the source. And she subtracted off the known source component based on the microlensing light curve, and then the light left over was the light from the lens. The other thing you can do is just wait a really long time. These things have a proper motion. Eventually they'll separate. But a long time, typical cases is a minimum of 5 years, I would say, probably closer to 10 or 20. And so that's harder to do and requires a lot of patience.
Given that many stars are in binaries, do you see microlens events around binary stars as well?
Yes. We see lots of binaries. I don't know what the exact proportion is, but when you have a binary perturbation, it's a lot stronger than a planetary perturbation, and so it really dominates the effect of the light curve. It's sort of like that first thing, the thing I'm showing in the lower left corner. It's like that, except 2 magnitudes, and like the whole light curve just looks like that. There's no underlying stellar event. It just kind of looks. It takes place over tens of days. Yeah. So we see lots of binaries.
Is there any effort to measure the spectra of the source star while the microlensing events are occurring?
Can you measure the spectra of the source star during the microlens event?
Yes, that is a really exciting thing about high magnification events. Thomas Bensby, I've been working a lot with Thomas Bensby and some other people to actually measure spectra of the source stars. What that gets you is that tells you about the stars in the bulge, and it allows you to take a spectra of dwarf stars that are normally faint. It does not actually help you at all in understanding your planet host, because those are all the lenses. Yeah, but the Bensby papers, Bensby et al. Is the thing to look up. Yeah.
Okay. If the source star has a planet, would the image of the source star and its planet be magnified in angular dimensions?
Yes, but it would still be really small. So it's hard to detect planets around the source stars for a variety of reasons. And was that the last question?
I think so.
Okay, well, I'd also like to thank Courtney a lot for helping me out and giving me direct feedback.
We have one more question.
Okay.
Thank you. Is there a chance to detect free-floating planets with microlensing?
Oh, I think I know the answer to this one. Is there a chance to detect free-floating planets with microlensing?
Yes. A free-floating planet event looks just like a single star event, except that because the Einstein Ring is much smaller, it happens much faster. And so there's a paper by Sumi et al. From 2011 in Nature, in which they detect an excess of events with timescales shorter than 10 days. And from that, they infer the presence of a population of free-floating planets. And hopefully Scott will talk a little more about that tomorrow.
Okay, thanks again, Jennifer.
Okay.
Thanks, Jennifer.